Today we're going to be talking about the history of light and the speed of light and why the speed of light is so special. We'll also be talking about the relationship between frequency, wavelength, and the speed of light. Uh, Lastly, we're going to be talking about the light's relationship to energy and frequency. So today's thing is going to be called faster than a speeding photon. So first off, let's talk about the history of light, and we're going to play this video.
There once was a guy named Albert Einstein, who you have probably heard of, and he developed the equation E equals mc squared, which you have probably heard of also. Using this equation, the relationship between mass and energy can be calculated using the speed of light, which is a universal constant. The value for the speed of light is exactly 299,792,458 meters per second. Now, this is the maximum speed at which matter and information can travel in the universe. But how did scientists determine the speed of light? Philosophers in ancient Greece were the first to think about and debate the speed of light. Way back in the 5th century BCE, Empedocles made the first claim that light had a finite speed. Aristotle, however, disagreed and said that light was instantaneous. Euclid and Ptolemy thought that light came from the eyes, which is what enabled sight. This would seem to imply that light must have an infinite speed, which allows us to see really distant objects like stars immediately upon opening our eyes. Over 1,000 years later, the Islamic philosopher Al-Hazin proposed that light actually travels from an object into our eyes, and therefore light has a finite speed. Like 600 years later, really smart people like Johann Kepler and René Descartes were saying that the speed of light must be infinite because there is nothing in empty space to slow it down, and during a lunar eclipse, the sun, earth, and moon should be out of alignment, which had never been observed. So for more than 2,000 years, the debate as to whether the speed of light was finite or infinite raged on. The problem thus far was that no one had developed an experiment that showed that light either arrived instantaneously or whether it took some time reaching its destination. But that was about to change. In 1629, Isaac Beckman proposed an experiment in which observers watched the flash of a cannon being reflected off of mirrors at different distances from the blast. The observers were then to tell whether the flashes arrived at different times. The problem was the mirrors were not far enough apart, so the experiment was inconclusive. Galileo came up with another experiment in order to determine the speed of light, in which two people with lanterns would stand a mile apart and take turns flashing each other with the lanterns, and then determining if there was a lag in the amount of time it took that light to reach them. There actually would have been a delay in this experiment of about 11 microseconds, which is way too fast for our feeble human senses to detect. So again, the results were inconclusive. It wasn't until 1676 that someone would finally prove the speed of light wasn't infinite. That someone was the Danish astronomer Ole Romer. Romer was studying Io, the moon of Jupiter, and its orbit around the planet, which took place every 1.76 days. Knowing this, Romer believed he could precisely predict the motion of Io. But he couldn't. He noticed sometimes Io seemed to be behind schedule, while other times it seemed to be ahead of schedule. But what was causing this apparent change in Io's orbit? Well, after thinking about it for a while, Romer noticed that the moon of Jupiter seemed to be behind schedule when Earth and Jupiter were farther apart in their orbit, and ahead of schedule when they were closer together. It wasn't that Io was changing its orbit at all, it was that it took light less time to reach Earth when Jupiter was closer, and more time when it was farther away. This must mean that light has a finite speed. But at the time, there were still a lot of doubters who believed that light was instantaneous. But like any great theory, Romer could use it to make predictions, and predict he did. He let his colleagues know that on November 9, 1676, Io's eclipse would happen 10 minutes later than they expected. When the time finally came, they were astonished to see the eclipse happen just as Romer foretold. And using what Romer figured out, the Dutch scientist Christian Huygens was able to calculate the speed of light to be 220 million meters per second. Whoa, but wait! We learned earlier that the speed of light was 299,792,458 meters per second. I mean, that's a good first attempt and all, but we still haven't answered our question. How did scientists determine the speed of light? Well, the centuries that followed saw many scientists performing many different experiments, from James Bradley in 1729 using the effect of stellar aberration to calculate a speed of 301 million meters per second, to Albert Michelson in 1879 using rotating mirrors to calculate a speed of 299,900,000 meters per second. But it wasn't until the 1970s, that lasers finally made it possible to start nailing down the speed of light. We all know lasers make everything better, duh. And using lasers, the speed of light was determined to be 299,792,456.2 meters per second. A decimal? Are you kidding me? Well, believe it or not, in 1983, the definition for the meter was actually redefined so that the speed of light could be a whole number. And that whole number is 299,792,458 meters per second. The speed of light as we know it today. So that's how scientists determined the speed of light. You see, that's the cool thing about science. Even if it takes years or decades or even centuries to answer the questions we have about the natural world, no matter how impossible they seem, there's no better way to go about finding those answers than with science. So stay curious, keep asking questions, and continue exploring the world around you, because there's no telling what discoveries still await us just around the corner. Thanks for watching.
All right. So as that gentleman was talking about, the Danish astronomer Euler Romer was the first person to take data from which the speed of light could be determined. Up until this point, there was a big debate on whether or not the speed of light was even calculatable or was or infinite. So he first proved that there was a speed of light. Then it was Albert Michelson. He became the first American to actually calculate the speed of light, and he came in with pretty darn close to the actual given value, and he was the first American to win the Nobel Prize for calculating the speed of light. Now, the speed of light, we name it the letter c. The speed of light is 300 million meters per second, or 3 times 10 to the 8th. Again, the symbol we use it is c, just like in the equation E equals mc squared. You take the mass times the speed of light, square that speed of light, and you get E. So that is the specific, that is very specific, and it is always true. The speed of light for light is always 300 million meters per second in a vacuum. For all forms of light. This is including in radio waves. That's in the same as going to be for microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. All forms of light have the exact same speed, and that's 300 million meters per second, or 3 times 10 to the 8th meters per second. Okay, this is really, really fast. Actually, if you were to travel this fast, you could travel around the Earth's equator 7 times in 1 second. It's that fast. Now, again, we want to state all electromagnetic waves will travel at the speed of light. This value is 3 times 10 to the 8th in a vacuum. Therefore, you can, in a formula, use this as the velocity of that wave, because remember, light is a wave, and we can find it using that same equation where the v is equal to lambda times f, but this time we're going to change out that v to being the speed of light, c, and we can change out that equation. It's the exact same equation as our last test, but it's now just c instead of just v. So you'll want to write that equation down. Now, the speed limit cannot go faster. Nothing in the universe can ever go past the speed of light. Einstein proved this, and scientists have collaborated with this. You cannot exceed the speed of light. Speed of light can decrease as you travel through different mediums. meaning that light travels through air, it will slow down ever so slightly. Travel through water, it will really slow down. But you can never go faster. Now, we're not going to deal too much of slowing down. We're always going to assume the speed of light for light is always going to be 3 times 10 to the 8th or 300 million. So let's do a practice problem. What is the frequency of a 404 nanometer light? Pause the video, try this out. Alright, so now that you've tried this out, you know that the equation is C is equal to F times lambda. We know the lambda is 404 nanometers. Nano means 9 times 10 to the 9th. So that's 404 times 10 to the negative 9th meters. So we rearrange this equation. We get C divided by the lambda is equal to F. We take the speed of light, 3 times 10 to the 8th, divided by 404 times 10 to the negative 9th, and we're going to get a frequency of 7.42 times 10 to the positive 14th hertz. Let's try a different one. Gamma ray bursts are objects in the universe which emit a pulse of gamma rays with the high energies. The frequency of the most energetic burst has been measured around 3 times 10 to the 21st hertz. What is the wavelength of this ray, this gamma ray? Again, we're going to do that exact same thing. So pause the video and try this out. All right, now that you've tried it out, let's look. Frequency is 3 times 10 to the 21st hertz. The equation again is the same one. C is equal to F times lambda. Rearrange it, so C divided by F times is equal to lambda. So the speed of light, 3 times 10 to the 8th, divided by 3 times 10 to the 21st, which gives us a nice value of 1 times 10 to the negative 13th. So, a portion of the visible spectrum, which appears brightest to the human eye, so the eye sees it the best, is 560 nanometers in wavelength, which this corresponds to a yellowish green. What is the frequency of 560 nanometer light? Remember, nano means negative 9th. Pause the video and try this out. Alright, so the wavelength again is 560 nanometers, 560 times 10 to the negative 9th. The equation stays the same, rearranging that equation, and we get 3 times 10 to the negative positive 8th speed of light, divided by 560 times 10 to the negative 9th, which gives you a total of 5.35 times 10 to the positive 14th hertz. That's the frequency of visible light that our eyes really are attracted to. Now, energy, on the other hand, is not the same equation. Energy comes from this gentleman. His name was Max Planck. He was a German theoretical physicist, and he discovered that energy is quantized, meaning that it came in small little packets. Later, Einstein, with the help of Max Planck, kind of gave it a name. They called it the photon. The photon is a packet of energy, and it had a very specific amount of energy. And Max Planck stated that energy was proportional to its frequency, meaning that if you increase frequency, you increase the energy. So as you move from radio waves all the way up to gamma rays, that your energy also increases. And so Max Planck, he added this equation. He created this equation. And he said energy is equal to H times F, where H is equal to Max Planck, that's equal to Planck's constant. And Planck's constant is 6.63 times 10 to the negative 34th. So all you do is you take the frequency, multiply it by this number, and you get the energy of that photon. So let's go back to that same yellow-green problem. This is that color. The 5.35 times 10 to the positive 14th hertz frequency of light, it corresponds to this kind of yellowish green, which is the most vibrant color our eyes can pick up, most sensitive to our eyes, and that's why safety vests are this color. So the same yellow-green color from the previous slide has a frequency of 5.35 times 10 to the positive 14th hertz. What is the energy? Well, again, we just take the Planck's constant, multiply it by that frequency, and I want you to try that out at home. Put it in your calculator, see if you can actually get the number. It's not important just to know that you can multiply, but you can actually put it in your calculator. So I'll wait till you do that. All right, so you get the answer is 3.5 times 10 to the negative 19th joules. That's how much energy is in one little photon, one little packet of energy. It's not a lot, but you got to remember each light bulb is producing billions and billions of little photons of light. So 3.5 times 10 to the negative 19th joules of energy. Remember, energy goes up as frequency goes up. You can kind of think of energy as the ability to cause damage or cause cancer. So as energy moves up from radio waves, doesn't do anything. There's no harm to it. Microwaves, nothing. And then you go up to visible, you use that for your eyes, but then you start getting to ultraviolet. Has a little bit more energy, can penetrate your skin, can start damaging DNA, but doesn't go too far into the body. It just does skin cancer. You can go up to, or even some burns. It can actually has enough energy to burn your skin. Then you move up into your x-rays. That has enough to penetrate your soft tissues, but not enough energy to penetrate bone. That's why you can take pictures. And if you get too many x-rays, it can actually increase your chance of getting cancer. And then you get your gamma rays, which have enough energy to go through the cells and damage and wreck your things and can potentially cause cancer. So lastly, let's go through some energy practice problems, and then we'll end this video. So what has the largest frequency of infrared or ultraviolet light? And then if you answered the largest frequency, again, it's going to be your ultraviolet. You can, again, always think about what's on that electromagnetic scale. It's always going to be towards your gamma rays, your radio waves over here. So your ultraviolet is closest to gamma rays. What is the largest wavelength? Microwaves are visible. It's going to be your microwave on the far left side. Radio wave, microwave, infrared, visible light, ultraviolet, X-rays, gamma rays. So microwave, your largest wavelengths are going to be on the other side. What has the fastest speed? X-rays or radio waves? Trick question. They both have the exact same speed. X-rays and radio waves have the same speed. They are both portions of light. Everybody wants to say, oh, X-rays travel faster. No, radio waves travel at the speed of light. X-rays travel at the speed of light. They both travel at the same speed. So don't get that mixed up. That's a trick question and a really good test question. All right, what has the largest energy, red or blue? Again, we're going to look at this. Red is nearest to infrared. Blue is next to ultraviolet-ish area. So our blue is going to be your highest energy. In fact, red lasers don't hurt your eyes. Don't stare into a red laser, but that's why they can give it to little kids. Blue lasers, very rare. You don't see blue lasers very often, and that's the reason is because blue lasers can damage the retina. And so that has a larger energy, a larger ability to cause damage. So if there's any other further questions, you can go ahead and ask your teacher. Thank you.